Hi everyone, welcome again to another Select seminar. Today we will have Leah Ye, who will be talking about the experiment of teaching select calculus to high schoolers, quantum in pictures, learning quantum theory in high school. And Leah, please take it away.
Hello, everyone. Today, well, as John said, I'll talk about the study. So this paper is on arXiv, but the one on Arc and published at the Quantum Science and Engineering Education Conference last year. But this is the pre-study paper, and we've also got a post-study paper that's we've finished drafting. So we hope to release that when we're ready. But just means that in addition to the pre-study, we can also talk a bit about our test scores and demographics analysis after the study. So this this is a collaboration between a number of institutions, uh, Continuum, the University of Oxford Computer Science Department, and IBM Quantum. So here's a number of the faces on the team. There are more people on the team, but these people were involved with the experiment itself or the discussions of the future plans. So I have these generic slides about ZX calculus, but this probably is not the right, is probably not suited to this audience. So this is just like a recap. So, and also I can comment about how much we teach the high school students. So in the high school textbook, it does, other than this scalar rule, this scalar being equal to 1, we don't teach them the scalars just because they weren't necessary for, and they're even not necessary for most people using ZX calculus in practice. So other than that scalar rule, which is just necessary for completeness, all of the other 7 rules that are here on this slide, that's enough for any qubit linear maps completeness, was in the textbook of the high school students in the course. But the Broadkin notation was not directly in the course, so not in the textbook, but we did provide with them, if they asked or had prior exposure to matrices or Broadkin notation, they were given the translations if they were interested. And of course, if they haven't learned that at all, it was not necessary. So although we did not do this in the course, one possible extension is to have all finite dimensional Hilbert space completeness. So just so that the students know that there is more general applicability of this formalism beyond just qubit stuff. The experiment had 3 main objectives, but the most important one was the test of which quantum concepts are teachable to this age demographic. So here, inside this brain, it's the zone of proximal development is this middle region. So this signifies which is the zone that the students can learn, which concepts can the students learn if they had some guidance. Around it are inside the innermost circle is that the concepts and the skill to which they can achieve them, the students can do independently without guidance. And the outermost one is that the ones that even with guidance are out of the zone that the students can attain even with guidance. So the key performance indicator, so how we tested this hypothesis of which quantum concepts was within this zone, was using a exam. This exam was at the end of the course. Of course, the whole course and the exam was entirely voluntarily done by the students. And every single question from the exam was from a past University of Oxford Computer Science Department postgraduate exam. So we do have the matchups of which exam from which year and which question from which exam for which year. Yeah. And the training that the students received, so the part that constitutes the guidance here, is these 8 lectures, which were pre-recorded. So it's a flipped classroom approach, and flipped classroom in education sciences means that it's an approach that's gotten popular in recent years where the students they have their lectures entirely pre-recorded so that the live in-person or interactive instruction in our case online, the interactive part of the instruction can focus on reinforcing those concepts instead of just like going through the definitions, for example. And it also frees up instructors' time so they could like reuse lectures, etc., and creates a more standardized lecture experience for each student. Plus, if the students can't make the live lecture, in this case, because it's a flipped classroom approach, they can watch the lectures on their own time, which is especially crucial because the students were doing this on an entirely voluntary basis on top of their usual courses or other like exam preparation or extracurricular stuff. So in their free time. So yeah, here's the textbook that was used for the course. It is the published in 2023 Quantum in Pictures textbook that's written by Bob Kuka and Stefano Gogioso. This Latin in the back is out of date, but this is just what the textbook covers looks like, except for the Latin. And the kind of interesting part about this textbook is that we were testing a new, in the context of education, formalism called quantum pictorialism. So this was the first time to do an experiment study that, well, involving human subjects that tested, can you teach quantum concepts using this formalism? And this formalism is entirely diagrammatic. So although there is mathematics and these mathematics are entirely contained within the diagram. So you could think of the diagram as an alternative axiomatization for learning these concepts. And by the completeness result of earlier, it does suffice to show any reasoning for qubit quantum mechanics. So here's just a side-by-side. The left-hand side of this slide is the image from the textbook as well as the lecture notes. And the right-hand side is a student's recreation of consolidating those concepts that was learned from the lecture. So representing that with these graphical formalism, you can take advantage of a 2D space to draw your information. So you can represent tensor product as space-time separation, space-like separation, well, just diagrams in parallel. And then processes happening over time at different time steps would be a sequential composition. So on the same wire, but going from bottom to top in this case. In this slide, we have the great fortune to thank Sarah for. This was Sarah's notes when she took the University of Waterloo's master's course when she was a master's student. And this is how she conceptualized and as well as, well, mainly just calculated the process of quantum teleportation. So the circuit on the top left, and then verifying that it does indeed teleport the input quantum state, whichever it is that Alice had. I should correct what I said. I'm not quite conceptualization from Sarah's perspective. So Sarah used this as an example to show that, in her opinion, the quantum teleportation circuit and this bracket notation calculation was not so intuitive and very intense with calculation. In contrast, with just the two ZX calculus rules on this slide, so fusion and identity, it suffices to show this graphical quantum teleportation proof. So this proof of correctness just only involves first doing these 4 fusions. And of course, that only connectivity of the diagram matters. So you can change the shape of the diagram without changing any of the connections. Then you can do more fusions. And your bits measured here are B0 and B1. So because they're bits, when you fuse these two, you get a total phase of 2 B sub 1 pi, which is both, which is 0 or 2 pi, depending on if B sub 1 is 0 or 1. But modulo 2 pi, both of that is 1. And finally, you can fuse one more time now for the green color, and that also goes away because B0 pi is either 0 or 2 pi, which mod 2 pi is also 0. And finally, you get the teleportation protocol successfully. I'll take a break here just to check if all of this so far makes some sense. I'll take more questions at the end. I'm just not sure if there's new faces at the moment. Sounds good? Okay. So Hamza and I made this rough list of the quantum concepts that are taught in the 8 weeks lectures. So I'll first point out that there was no mathematical prerequisites, at least not in any conventional sense. So from the high school perspective, there is no matrices, no bracket notation, no tensor product, no complex numbers, and no trigonometry that was necessary to cover all of these below concepts here on this slide. So on the left half of this slide, so I'll just kind of go down the column. We have space-time diagrams as shown on the previous slide. Process theories and Choi-Yamokowski isomorphism. We don't call them Choi-Yamokowski isomorphism to the students, but we do provide the translation. It's at the back of the textbook for those who are interested. But this just means wire bending in the graphical formalism. But it's something very non-trivial in bracket notation. We also have quantum gates for any multi-qubit or qubit gates. This is a universal gate set. We have reversible computation, so the idea of unitarity will be reversibility, which for quantum gates is equivalent to unitarity. We have states, circuits, quantum measurement, and post-selections. We have complementarity of C and X observables. So that's green and red in the graphical calculus. And I think the calculus is most effective at expressing entanglement because that has a very conceptual graphical meaning of just connectivity between multiple qubits. So entanglement, Bell states, and Bell measurements. So Bell states, as shown in here. So this circuit, you could have rewritten the Bell state to be just this cup, and this Bell measurement is just this cap with this B0 and B1 C and X rotations possible depending on what B0 and B1 were on the measurement. Deterministic versus non-deterministic processes. So we also could say this more precisely by using the terminology of sure boxes to say that this is a deterministic process. And uncertainty principle, which specifically the Stern-Gerlach experiment was one of the most specific examples of that. And on the exam, we even included the most conceptually difficult question on the exam was about multi-party quantum communication protocols. And finally, mixed state quantum information. So this was presented to the students with doubled wires and singled wires. But this suffices for any completeness of all multi-qubit mixed state quantum mechanics. So this slide is just mentioning some possible future work that we'd be quite interested in, but aren't quite so prepared to do so yet. But as young as age 10 has read the book and I gave it a quite enthusiastic review. So there is the possibility that in the future, this approach could be used to teach even younger ages as well, even though in this case, this was the first time to test it on any age group at all, specifically high school. So to go over some of the experiment parameters itself, here's the selection process. On the left-hand side of this slide is a flyer that we made. One thing I'll notice is that I'll make note of is that upon completing the course, you will receive a certificate and your own copy of the textbook. So we think that even though as with studies with human subjects, sometimes it'd be common to reimburse the students for their time, reimburse these subjects for their time participating in the study. But in this case, they are receiving a free course. And also, I think we could tell that for many of the students, this was not only a good opportunity to learn, but also could give them some expectations about learning more about quantum information and quantum computing, as well as to improve their prospects of university applications. and also go out of their comfort zone to learn a new subject that usually is never covered in high school. So, and also some quite long quantum computing courses available currently to the high school level usually has a tuition of a few $100s. Rate depending on how long the course is would be a few $100s. So we made the course free. But we did have quite limitation in how many students we could support. It being a study, but we also needed to make sure we had enough tutors to have a good tutor to student ratio, as well as enough people to mark all the exams and have a good quality of the course. We wanted to have about, so I guess typically in statistics, people say about more, at least you need at least 30 participants of a study to say anything significant about the results at all. So accounting for some bit of drop off, that means we should target, we weren't sure in advance how many students would drop out. For example, for MOOCs, which is massively open online courses, sometimes like 90% of students drop out, but those are like, so with online courses, it's really hard to predict how many students would drop out. But we actually had a pretty amazing retention rate, which is that out of the students that we received over 1,000 applications. We couldn't take them all, of course. We just had to do a random selection, just controlling for certain factors such as that everyone's from UK and is in high school, and is the main thing was having people. Majority of the students were from state schools, just and geographically spread out across the UK, so not all from the same private schools or something like that.
Um, can I
Hello? Yeah, go ahead.
ask something about the select? So they were randomly selected, but I'm assuming those 734 people actually applied to this. Like they're not a random subset of all high school students. Did you
That's
do
correct.
any kind of selection to make sure that their grade average sort of matches the national average, for instance?
We did ask them for their grades. I don't know how that compares to the national average because it also depends on the high school specifically that they're from. It is true that students who volunteer for this kind of course are going to be the more self-motivated ones, and some of them may have some prior knowledge of quantum, although our survey says that almost all of them, most like super majority of them did not have substantial knowledge in quantum according in their self-perceived way. Um, so the students, well, because it's a voluntary study, we can't force high school students, especially they're minors, so they're like under the age of legal consent, uh, or they're under 18, so we cannot force them to choose such a course. So we can kind of ethically consent-wise, the only option is to do, had to have it be applications, and then we randomly select from that. The alternative way would be to approach teachers and then have the teachers volunteer their students. That could also be an option, but then that is a lot less. Then the data would be of lower quality in some ways because in the main way, because now it's one specific school, one specific teacher's class, and not a representative of randomly selected students all over the UK. So these were factors that we considered, but I don't yeah see much other way we could have done it without while fulfilling these criteria.
Okay, thanks.
So I should also note this was done during a summer, so school is not in session either. um yeah. So we didn't test their fluency in English. We just like asked to check that they were okay. It was just like a yes, no, are you guys okay with the course being in English? And we had 54 participants complete the course, and this was defined as submitting an exam, a complete exam at the end of the course. But also attendance-wise, we had about 50 something students who were maybe I think high 50s or low 60s students who stuck through the whole course. So here's the left-hand side of this figure is the participants' pool's ethnic demographics, and on the right-hand side is their self-reported what kind of school that they are from. So I guess the notable part is that 30 out of 54 of the students were from state schools in the UK. So this is in the US, this would be called public schools. It just means like the government run like usual schools that students attend. The schools that the most common kind of school. So not privately run schools. And like non-boarding schools. And on the left-hand side, this demographics, we can see that it's quite spread out. So we do have a very diverse ethnic makeup of the students in the course. The learning materials, so as I mentioned earlier, the flipped classroom approach. So here is screenshots of just 4 of these videos. And the plan is to release these videos publicly available online, hopefully quite soon. So this was done on chalkboard with some computer editing. And it follows the textbook pretty directly. The course covers almost all of the chapters of the textbook, but not all, just because I'm kind of focusing on quality over quantity. And there was a few quizzes spread out throughout the course. I don't know if it was 3 or 4. So these quizzes were chances for students to test their own knowledge independently on their own. And then afterwards, after some time, they would then release video solutions of it. So here's the test results. Quite exciting is that we were quite blown away by the exam scores because at least I would say from my perspective, and probably most perspectives of people running this course, is that because this kind of experiment has never been done before, we have no idea how well the students are going to do before they take the exam. Like we can kind of have some kind of idea of how much they understand from the tutorials, but that's not the same as like the amount of information you have from doing an exam. And also because these questions were just translated from postgraduate exam questions. So University of Oxford past year's master's and PhD level course taken by master's and PhD students or 4th year undergrads, which is in the UK is like master's. These exam questions were almost identical to the ones on this high school course. I guess I would say the 2 main differences is one is like it was translating the terminology to the high school student terminology, but then the course itself, just like the jargon translation, but then the question itself being the same. And the second difference is to not muddy and introduce a new variable. It was tested. We removed this one small part of one question that asked about probabilities because it's likely that the high school students, especially those who are in the 1st or 2nd year of high school, has not learned probabilities in high school, and we didn't want to muddy their understanding of quantum information by introducing this additional variable about whether they've learned probability or not. So the exam scores are quite brilliant. So here it's kind of one with a filter and one not on this slide. On the left-hand side, though in bold is the numbers for students who we counted as participants. So this is over 4 and 5 out of them passed, over 80%, and around 1 and 2. So it was either, I think it was 48 or 49%, got a distinction, which in the UK, a distinction is the highest grade category. So the UK grading scale is that I think 50% is a pass, and then 60% is you're doing pretty good, and then over 70% is distinction, which is the highest grade score category in the UK grading system, as well as at University of Oxford. So this is much better than, well, I don't have the exact numbers because we don't have question by question breakdowns of past years' exam scores for the Oxford postgraduate course, but this is better than the graduate level scores on some of those past years' exams. Which we don't yet know why or any hypothesis, except one hypothesis that we have, but is that maybe it's because the graduate students has already learned different formalisms or has already learned more, and they might have to unlearn that. And a different hypothesis could be that the content that the graduate students had to handle was more because the instruction time was more, because you could think of like this graduate students were doing 1/3 of their time in the course, one third of their like academic, their main thing is to take these courses during those terms. If they take if they take 3 courses a quarter a term, then when one of them is this, then that's 1/3 of their total studying time. Versus for these high school students, they're doing it in their free time. It's not going towards their school grades. Some of them are working part-time jobs and these kind of things. So some of them were working part-time jobs. Almost all of them had exam preparation because that's what is really heavily factored into their university admissions and so on. And also that made the lecture time also shorter for the high school students. And it wouldn't make sense realistically to cover exact same amount of material as you would cover in the graduate course, but it gets really far. So I'll comment about this non-bold numbers, the ones with the 4 pointed stars instead of the 5 pointed stars here. So this is just a technicality, but we had a filter which is called a canary question according to University of Oxford tradition and usually practices, which is to have a really easy question and a really hard question on the exam. So that kept spread out the score distribution more to see to better understand how much the students mastered or didn't master. And specifically, the canary question meant to be an easy question kind of shows is intended to see which students put in enough effort to even understand the basics. And in this case, we chose the canary question, which was also a question on a past University of Oxford postgrad exam, to be just a spider fusion for mixed state quantum mechanics, so with one double wire and then single wires. And this was also a definition that was from the last third of the course lectures. So this was basically a litmus test. Did the students watch the lectures or not? Because if they didn't, then we could say that they haven't really completed or participated in the course enough to recognize that this was a definition that we covered in both lecture and the tutorials. So even considering that for example, students were incentivized or just rewarded for just turning in any exam at all, even if they didn't do well on the exam. So we wanted the students to have a participatory experience to be rewarded for their participation and hard work, even if it didn't amount to them understanding the basic part. But actually, almost all of the students were able to get this canary question. So even considering this canary question, we have even considering those who did not pass the canary question, we have over 35% distinctions. And this distinction percent still exceeds the fail percent. So that's still very good performance. So with that said, we are quite confident that the hypothesis, confident in terms of statistical variance, quite confident that the hypothesis that these quantum computing concepts are within this zone of proximal development for this age group of 16 to 18 is correct. And I will say that the exam actually does cover most of the topics that are back over here. So most of the topics here was tested at some point during the exam. Of course, we couldn't make the exam very long, so some of them are just kind of very vaguely on the edge being tested, but it was definitely tested. So yeah. So we unfortunately can't release the exam questions yet, because we want to do some follow-up studies, and this being a baseline would allow us to compare different studies, especially across different countries or different kind of teaching approaches or other kinds of comparisons. So, but in the future, we hope to release the exam questions. I hope so. Yeah. So here's just the bar chart of the distribution of the exam scores. The blue is for all students, and then the orange is for those who also passed the canary question, which is most of the students. So, almost all of the students who did not pass the canary question failed the course. And let's see. So one thing is kind of interesting is that kind of roughly this is a trimodal distribution, which is also quite typical from the way that these exams at the University of Oxford are designed from according to Stefano, because of the way it's designed to have canary questions and like most of the questions, and then also the hardest question. One thing that's kind of interesting is that there was not really correlation with the students' exam scores and with the amount of time spent studying in the week, as well as their self-reported school grades in maths and physics. So this kind of means that quantum concepts taught via this quantum pictorialism approach is not needed to be kind of very sequentially, as is traditionally regarded in education, to have in physics education, a very sequential layering of concepts that you first learn this, then you learn this, then you learn this. That's kind of easy for school curriculums to do, but because of all these dependencies, it means that it's a really, really high barrier to learn these subjects. And if you kind of miss the bar very early on, you can be shut out from these subjects in the future. It'd be really, really difficult to gain confidence as well as the basic concepts and skills in order to enter the subject later on. So on the right hand of this side, we have okay, let's see. Okay, on the top right of the slide, I'll just kind of go through these figures. This was asking the students what is their prior experience and prior knowledge of quantum. And for about almost a third, it's almost nothing, no knowledge of quantum. And then for just over half, it's very limited knowledge of quantum. But on the right half, on the bottom of the slide, is that most of the students, in terms of time spent studying, I think this is external to the lectures and tutorials times. So majority, almost 2/3 of the students had 1 to 2 hours a week of study, which is also the kind of expectation that was set in the course guidelines at the beginning of the course, like of how much they could expect to commit for this kind of course before they signed their consent to be in the study and take part in the course. And on the bottom left is quite interesting. So 100% of the students said that they had to prepare for exams because that's pretty much the most important thing in their university admissions, one of the most important. And then more than 1 in 5 has a part-time job. So students send me email like, oh, I can't make my tutorial anymore because I'm called into work. And more than 1 in 10 also had internships. Others had other kind of extracurriculars or some kind of camps or vacation time or these kind of things. So this is kind of something to keep in mind, is that the students were quite busy. And this slide is about the impact of the course. So about 9 in 10 of the students agreed that this course motivated them to pursue a STEM career, and almost 70% agrees that this course strengthened their motivation and confidence. One thing is that not all the students may have wanted to pursue a STEM career anyway. Some could be taking this course out of curiosity or just wanting to learn STEM, but not necessarily so sure that they're pursuing a STEM career, especially at the beginning of high school. So for those who are 16 years old, they're not necessarily thinking or sure about their careers yet. But and there's some comments here about the tutor's communication and teaching style. So more than 70% of the students thought that the communication teaching style was good or very good, which is good from kind of in retrospect, because during the course, it was harder to judge this because it was very online. It was 100% online course. This kind of was inevitable because we wanted students from randomly all over the UK. And so there was no physical location that could be possible to do such a course. And so there was challenges with this online course, definitely using 100% Microsoft Teams to do the courses. and then not letting the students talk to each other, like only letting like entire all the communication outside of the tutorials being through email. There was some things that we wish we could have changed, but we had to get University of Oxford Computer Science Department and MPLS ethics approval to run such a study, especially with minors. So so we had to apply for this a year in advance. So we couldn't change these parts, and we had to just go with what the university allowed. But despite all this, it still worked out pretty well. So, um, but in the future, we would want to kind of convince the university to let us use Discord or something like that. Lastly, I think this is, let's see. Oh yeah, this is the last slide of data and then the summary slide. It's the future slide, sorry. And then here, this is just saying the student's age. So we said 16 and 19, but in the UK, the oldest university students are going to be 17 and 18 for the most part, and for most usual circumstances. So, and they had to be at least 16 because of the ethics approval, because there's a different process involved if you have anyone under 16. So these 16 to 18-year-olds, we can see that the score decreases slightly with age, by like 20%. Although we have much fewer 18-year-olds because of that's kind of the end of high school, so that doesn't tell us so much. Also, it doesn't tell us so much because the one hypothesis is that it could be that older students don't do as well. For some reason, for example, if they are having to juggle other responsibilities, or if they have learned other maths and so have to unlearn some of that, or if they're just about to apply to colleges, so their exams are the most important at that time, or they maybe care less because they know that or the opposite, that they've already applied to colleges and so their exams might not matter. I'm not sure, but I don't think this is so surprising, given that this is a phenomenon for end of high school. Some people call it senioritis, but anyway. So one really interesting future work would be to investigate the age factor more, especially not just at which age, at this age, students can learn these concepts successfully in this zone of proximal development. And a different question would be, what is the lowest age that these students can learn these quantum concepts and master these skills? So that would be quite interesting future work. Finally, yes, this last slide, some future work and ongoing work that's happening. It says quantum pictorialism will be taught at high school level in Greece this autumn 2024. It's actually started a month ago, so that's very exciting. So the Quantum and Pictures textbook has already been translated into Greek. And in addition, there's currently a quantum pictorialism course given at NUST University in Ghana, given to university students and professionals, so undergraduate, graduate, and professionals. There's plans to teach high school students in Denver public schools, and there's also plans to develop quantum games and museum exhibits and maybe science fair involvement to do more outreach as well as more gamified fun parts of giving more students the chance to have exposure to quantum concepts. So that concludes the talk.
All right. Thank you very much, Leah. Very nice talk. Do we have any questions in the audience? Yeah, so for me, like I would have really liked to see the exam questions, but I understand if you can't make those public yet because well, follow-up research.
So these exam questions, the past exam questions are available to people with the University of Oxford login, the past postgrad exam questions. I don't know if I don't know if the team is able to share the questions on an individual basis, like because I know you're not a high schooler, and you probably won't share them with high schoolers, but maybe there's just some blanket policy that it's probably easier not to share the exam questions with anyone, just to like not just the risk of it.
Yeah.
It's even the possibility we could mess up the future exams, but so the students were given 3 copies of their certificate. One is just a completion certificate that doesn't say their exam score. One has their exam score, the number out of 100%. And then the last one is which score category. So distinction or 60 to 70 or 50 to 60, these kind of things. So that way students could choose which one they most preferred.
Neil, you have a question?
Yeah, so I mean the whole design seems very, very well thought out, unsurprisingly. Um, and I guess one thing that I wondered is if you wanted to include, say, teaching people about probabilities. First of all, as you say, you want to be sure that they have some idea about probabilities to begin with. Um, were there any thoughts in future experiments or future approaches to teaching quantum using ZX in sort of this way, how you would approach uh, coming up with actual probabilities for the different outcomes?
Yeah, I think it is quite straightforward in terms of how I imagine we could possibly do it. It's not the future studies methodologies are not set in stone yet, and we would write them down before, usually in experiments involving human subjects, especially. So in social science, you would first write a paper that spells out the methodology and get some feedback upon it, even put it online so that you don't just cherry pick and curve fit your data, but rather you've said in advance what you want to test. So that's why we have a pre-study paper that's published for this study. And so I think the best way would be going forwards would be, say, the Denver Public Schools upcoming study. That could involve, because it's one school district, so they've got a standardized curriculum across the whole school district rather than kind of across the whole country. So there's a lot more understanding of what the students has or hasn't learned, as well as if teachers are volunteering their students from specific classes, then the teacher will know exactly what kind of probability they've covered or not covered. So that's one thing, is that just having more geographically and having students with the exact same educational background would cover that mystery of the probabilities. The second way to solve this mystery is with a pretest. So having a pretest that tests specifically probabilities would help with this. And it would be also interesting to add other things to pretests as well.
Do you mind if I ask a quick follow-up question?
Yeah, of course.
Okay, so this might actually be a bit too speculative, so feel free to say if it is so. Those sound like very good experimental designs, but I was thinking about the approach that one would take if you're missing out scalars to actually talking about the actual probabilities.
I think that would just add the scalars back in. I think that would just add the scalars back in. I mean, that is done for the postgrad course at Oxford, except for almost all of the problems, they don't need to keep track of the scalars, so they just use the rules up to scalars. But in very specific cases, such as with probabilities, they do need to see the scalars. So that just be in a so the students were given a cheat sheet for the exam, these kind of, here's some basic rules. But also University of Oxford students also have a cheat sheet for the exam because they're open book exams. So this is pretty standard practice. And so these scalars would just go on the cheat sheet. He would also add a tiny bit to the total lecture time to have the scalars in there, but I think it wouldn't be so bad, except that calculation-wise, the students would have to keep track of more.
Mm-hmm. Right, thank you.
Also, we taught the meaning of the scalars more precisely. So I think scalars are covered up a bit in the textbook. So the curriculum is already there for it. It's just I've kind of made the choice to not dive so deep into it because it's kind of a lot of calculation for not so much benefit.
Mm-hmm. Right, thank you.
I was a bit surprised to see that there wasn't a correlation with the mathematics grades. Like, I could believe that there is not a strong correlation with the physics grade, because physics education in high school has quite a different focus, like much more numerics and filling in stuff and formulas. But sort of with the mathematics, sort of like this formalized rule following, right? Because like you give students a couple of things they're allowed to do with diagrams, and if they do other stuff with diagrams, they get the wrong outcome. And this like sort of abstract reasoning, like I would expect to be correlating quite strongly with mathematics. So I'm quite surprised that wasn't the case. And I wonder if you have any thoughts on that.
I'm not so familiar with the UK high school mathematics curriculum, but I do know that maybe like 1 in 10 actually learns and get tested on matrices, and almost all of them don't. So at least when it says mathematics, when it says a student's mathematics grade, it's not talking about stuff like matrices, because that's for most of them, they wouldn't have formally learned matrices yet. Especially most of them were kind of the younger high school students, as opposed to like 16 or 17, not rather than 18. Well, not the youngest, because below 16 we couldn't.
Yeah, but still, like in algebra, which I'm pretty sure they would get, like there you also have like certain rules you're allowed to follow, and you need to follow them, otherwise you get the wrong outcome. Like it seems to be kind of the same kind of skill. Like you have the abstract symbols that mean something else, and you have like certain formalized rules you're allowed to apply to them.
Yeah, I guess one of the examples would be variable substitution in algebra. That graphical substitution is like that. So it is interesting. We don't have an explanation for that. Um,
Or is it maybe that the kind of people that subscribe to this experiment, like they want to do the experiment, are already above average good at mathematics and physics, and therefore the variance is already accounted for? Like if you were to test people who are actually bad at mathematics, then you would see that mathematics skill is correlated with this, but they're already pre-selected because they're the type of people who want to do an experiment like this. So maybe that's the reason that you've, yeah.
that's quite possible. We did try to make the flyer really, really welcoming. So like have kind of cute pink and purple colors, and like color of Dodo, and like a picture of Dodo, and these kind of things to make it not seem so technical.
Mhm.
And make clear it's about the quantum world in pictures. But these are things we could test in the future.
Okay. Titwan, you want to ask me a question?
Yes, I'm curious. So I think you had the occasion to teach also at a university level, right? CX calculus and this kind of stuff. So did you witness some difference between what was I don't know, the main difficulties of the student, depending if they were high schoolers or older students? And I'm very curious also to know that. So I had to do the calculus to university student as well. So for high school students, what was the most difficult part learning the calculus?
Uh, let me think. Some of our difficulties were not from their conceptual understanding, but some of it was just like technical difficulties, such as sometimes the students randomly disappear. They say, "Oh no, sorry, my Wi-Fi disconnected," or like because it's fully online course, and then sometimes like it would be on Teams, and then so if their screen is black, you don't know who's listening or who's not listening unless you ask a question. So we try to make each tutorial have some interactive component. But and then sometimes we'd have them try to draw a diagram to answer a question during the tutorial and show it, but maybe they'd spend some time like getting stuck how to upload the diagram and get stuck there. Um, in terms of understanding, that would be interesting to do some one kind of future thoughts is to do some more interviews. So to do interviews with students to ask them which parts that they felt they struggled with, or and ask and kind of that fewer data, but qualitatively figure out what's the conceptual parts. Because what exams are good at is quantitative data, but doesn't show much insight into the students' lines of reasoning and how they arrived at a wrong answer versus a right answer. As for conceptually, what was difficult, definitely the computation took some while to get a hang of. Surprisingly, so when once this kind of not answering your question, but most conceptual question on the exam, the second question was a multi-party, multi-step quantum communication protocol that was like you start with an entangled resource state, and then you're allowed to do these kinds of operations, local operations, and then you want to produce this kind of entangled state in the end between the remaining parties, for example. So this kind of question was, we thought that it could be really difficult because this was not a computation question. I mean, there was a tiny bit of computation, but it was mostly about the conceptual understanding of stuff. And the students did quite well on that question. So that doesn't tell, because the students did well, it doesn't tell us what parts the students didn't understand. So that would be interesting, maybe increase the difficulty of future qualitative sessions. To do it on an exam would be a bit mean because as well. It's also for the students to gain confidence, and giving them too hard questions, harder than the University of Oxford postgrad exams, would be just really mean. Yeah, so this would also be something interesting to investigate.
Yeah, so I see. So accepting the final exam, in fact, you had not a lot of feedback during the experiment with the online thing, I think.
Yes, as well, we were allowed very limited allowed interactions with the students. So all of our interactions had to be via email or those tutorials. So
Okay, I see.
so the possibility of interview was not in this study proposal.
Okay, thanks.
Okay, do you have any more questions in the audience?
I can speculate a bit more about Tijuan's question, but it's because this is more like personal impressions of tutors. It's not so qualitative, so I can't say it so confidently because it's just impressions. It's interesting.
Okay.
I think mixed-state quantum mechanics is really, really well tackled by this formalism because it's so computationally unwieldy in other formalisms. Just taking out a product is just you just these gigantic matrices if you wanted to do it that way. I think it's also really great for entanglement and stuff with tensor product because you just got way more compact notation as well, which you could still do all the reasoning with. I think it's not so good with superposition. Depending on which quantum concepts, some proposed quantum concepts don't propose to test superposition so much, and it's not as clear how you would test superposition so much other than like bracket or matrix manipulations. Because it's the kind of basis dependence. You could say that some superposition, I think some superposition is not so well expressed in CX calculus because you're kind of folding up the sum of the computational basis within the other color, for example. So that's not something that I think is so well presented in this formalism. But you could say that every formalism and learning approach, teaching approach has different advantages, and they're also not mutually exclusive.
So I maybe have a last very general question about this whole process of doing a study with some clear results. How useful do you think it is? Because even as a teacher, it would have been useful to me if you had made, I don't know, small workshops with a few high school students and then be able to discuss with them, interact. Of course, we would not have any scientific results, but it might have been more useful in practice for the overreach of the X calculus. I don't know. What is your opinion on that? Maybe the overall motivation of the things. I'm sorry, this is a very mean question, I know.
No, it's not at all a mean question. It's a really good question. I have to think about it for a sec. I think that really different people have extremely different definitions of usefulness. And it's also kind of also what you have the ability to offer and what the students have the ability to learn and time-wise and all these different constraint satisfactions. Like for example, there's kind of this dichotomy, this kind of division in quantum education versus quantum workforce development, which is really interesting. It's like on one side, you have people really wanting to teach and learn and very, very focused on the understanding and kind of very more traditional classroom concepts. And like say first master the basics and all the understanding and the concepts. And then on the other side, you have this workforce development, which is a lot more, I guess, politically oriented language or saying that, like you're not talking about individual students or teachers or classrooms. You're talking about this nation needs to teach this many, needs to create this many jobs or this kind of stuff. Which I don't know much about workforce development. But depending on who is depending on what is your objective, what is your motivation, you'll have very different definitions of usefulness. So some people's opinion is that the high school, so opinion, not mine, is a common opinion is that, quantum information is graduate level stuff. It's like for people with PhDs. So what we want to do is just get high school students excited about science, and they don't need to actually learn the specific concepts or the specific maths or physics, but just to get some exposure and possibly want to choose these directions. But sooner or later, later on, they will have to learn the physics or maths. And some other people, so that's like kind of more outreach side. Some other people will be like exposure to the kind of career pathways. We did have a career pathways workshop as part of the course, to gain exposure also of the broader picture of quantum computing hardwares and career pathways. We had two career pathway kind of oriented workshops in the course. And sometimes you would say that project-based would also be better for learning, but project-based is not useful for a study and it doesn't kind of, so, and also they would have to learn enough first to be able to take on a project. And project-based is extremely demanding from the time of the people who are mentoring and running these projects. And it might be unrealistic for high school students who are kind of able to devote maybe 3 hours a week to this. Like if you matched up the lectures and tutorials and the study time, that might not be the best use of time. So there's a lot of factors, and it kind of really depends about what's useful. But I think what really is interesting about this study is that it kind of challenges the kind of defaults notion that a lot of people have, which is this intimidation part of quantum information, about how for many high schoolers or even many people at all ages, it's like very intimidating to learn quantum computing and quantum information. Is that usually it's like there's this image of it being like a for genius kind of for geniuses, or it's very it's like meant to be mystical or esoteric. Even in some languages, super majority of the search results will be like quantum mysticism and quantum healing, and then you'll have a lot of like I think it's good for quantum literacy, for quantum, which also is a terminology that's kind of gaining ground in quantum education. It's just like computer literacy, but now quantum literacy. There's also ongoing developments for that. So depending on your motivations, what people view as useful is going to be quite different. That's just one kind of slice of the cake, I guess. But I hope it gives some insight. And this is all parts of education, I guess. It's all part of these educational like total experiences, I guess. They're all needed.
Okay, thanks. Yes, this is a very open question, of course. We could talk for hours. But...
Yeah. Thank you very much for the questions. It's really interesting.